Alright, hello class. In this video we're going to be looking at what I call, say, advanced trig rules. Okay, and specifically it's to give us more versatility when we, deal with more combinations of trig functions. Okay, so typically what we talk about here is if we have, say, a sine raised to some power times a cosine raised to some power, or a tan raised to some power times a secant raised to some power. And there are various other ways you could go about it, but these are the two main ones that I think are important for getting the idea of the technique. Once you get it for sine and cosine, you get similar things for tan and secant. They follow in a very similar way. Okay, so let's start taking a look at how we do this. And what we essentially need, though, is definitely using identities. Okay, so there are a couple of identities we need for this method. Okay, so let's remind ourselves of what the main identities we need are, and then we'll break down the two separate cases for sine and cosine to get started with. All right, so the main identities that we use for advanced trig rules, one shouldn't be that surprising. That's the Pythagorean identity. That's that sine squared x plus cosine squared x is equal to 1. And specifically, we use the versions where one piece is moved over. So sort of like the cosine squared x is equal to 1 minus sine squared x. Or sine squared x is equal to 1 minus cosine squared x. We've used this one before, I'm sure, in this class, and if not, I'm sure you've seen some examples of this in Calculus 1 as well. What you may not have seen through your normal calculus is the half-angle identities. These will also show up in these methods, so they're ones I think a lot of people kind of forget about, but we can also rewrite sine squared x not just as 1 minus cosine squared x, but also as 1/2 times 1 minus cosine of 2x. So what this identity does is it rewrites a squared trig function as a non-squared trig function. Okay, so that's actually quite important there. Here, for the Pythagorean identity, what we're doing is rewriting one squared trig function in terms of the other square trig function, whereas here what we're doing is we're actually getting rid of this square. Okay, so sometimes we'll need to do that in integration, is getting rid of the square. Now, notice also that the pattern here is pretty much the same except for the sign. And how I remember this, I just remember the overall pattern, and I just think, oh, well, the cosine gives me the plus, and the sine, since it's different, gives me the minus. Okay, but both options give us a cosine of 2x. All right, so here's essentially how this method works. We're going to look at the powers a and b. Okay, so powers a, that was terrible, and b, and what we're essentially looking at is whether they are even or odd. Okay, and it turns out if one of the powers is odd, so if one power is odd, and we only need one of them to be odd, okay, then the technique is we break off part of that piece that's odd. So we break off one of the odd pieces, and I'll show you what I mean by that as we do it. I think it's easier to just show this method with an example versus trying to explain it in words. But basically, if one power is odd, we can break an odd piece off to set up a u substitution Okay, provided, oh, not provided, but sometimes we need to do multiple Pythagorean identities. So we set up a U substitution, possibly with multiple applications of the Pythagorean identity. Okay. Now, that's actually the easier one to do in practice. It's the harder one to describe in words. So that's our first possibility. And our second possibility is the worst one, and if both powers are odd, if both powers are even, then our only course of action is to use the half-angle identities multiple times until it reduces down into something we can integrate. And again, I can probably better show this through an example. So we'll just use a bunch of half-angle identities until it reduces down into an integrable form. Okay, so since I'm promising here that this hopefully makes more sense through examples, let's just look at some examples. Okay, so in this example here, we have sine squared x times cosine cubed x. So one exponent is odd. So here we have an odd power. So our technique here is to break this up. So break off a piece. And it might seem strange what that actually means, but what we're going to do is break this up into a cosine squared and a cosine. So we're going to break off a cosine. So let me write that. We'll break off one cosine. Okay, so when we do that, we're going to leave the sine squared x alone. Okay, and then we will have cosine squared x times cosine x dx. Okay, so that's what I mean by we break a piece off. We break one of these cosines off. And how we set up this U substitution is we want this part we've broken off, we want that to be our du. Okay, so I'm going to write that here. I want my du to be cosine of x dx. So now that tells me what I want my u to be. Because if I want my du to be cosine, that means I want my u to be sine. Okay, so if we choose or let our u be sine of x, then our du is going to be cosine x dx. And that's how this method always works if we have a single odd power. We break off a piece from the odd power, and then we're going to set up a u substitution with that broken off piece as our du. Okay, that's how this is always going to work. And then from there, and this is the part I think that makes this tricky for some people, after that we need the rest of the integral to be just in terms of sine. So I'll say to be only in terms of sine of x. And that could be sine squared, sine cubed, whatever, just powers. I'll put a little p here because it could be powers of sine, but we need to get rid of the cosine here because the cosine is our du. We want everything here to just be in terms of u. Now this part is fine, right? This is sine squared, so that would just be u squared. So what we really need to do is we need to adjust this cosine squared. And this is where we use the Pythagorean identity. Because by the Pythagorean identity, this integral, okay, I'm not going to do the u substitution thing yet, but it will be sine squared of x. Okay, I'll do this in yellow to match up here. Then my cosine squared becomes 1 minus sine squared. Okay. And then the cosine of x dx part stays the same. So now, when we look at this, this cosine x dx is still going to be our du. Okay, but now this sine squared x is our u squared, and this that we just made, so we changed the cosine squared x to a 1 minus sine squared x, so this will actually end up being 1 minus u squared when we do the u substitution. Okay, so here in this next step, let's do that u substitution. We're going to get the integral now of u squared times 1 minus u squared du. Okay, and now we have simplified this down to a much nicer thing. So now I'm going to distribute this u squared to get the integral of u squared minus u to the 4th du, and now we can integrate. All right, and the only thing we need to make sure that when we integrate is we put our x's back in at the end. So I'll go ahead and stick with the orange. The integral of u squared is 1/3 u cubed. The integral of u to the 4th is 1/5 u to the 5th, and we'll get our plus c. And now all we need to do is put our x's back in. So the u up here was our sine of x, so we just replace our u's with the sine of x's. So we'll get 1/3 sine cubed of x minus 1/5 sine to the 5th of x plus c, and there we go. Okay. Now I'll leave it up to you to check, but it would be a good idea usually to differentiate this and see if you get back to the same thing that we started with. Okay. Okay, here we have another example. In this case, both of my exponents are odd. So it really doesn't matter which one we choose, we just need to break off one of them. So since last time we broke off a cosine, this time let's just break off a sine. Okay. But at the end of the day, it really doesn't matter. Okay, so I'll get the integral of, this will be sine to the 10th of x, okay, times cosine to the 17th of x, then times just sine of x dx. And just like last time, this part that I broke off, I always break it off and put it all the way in the back because that's always what I want our du to be. Okay, so this tells me that my du I want to be sine of x dx, which means I want my u to be, well, to get exactly sine of x dx, okay, I would need a negative cosine, but I'm probably not going to have that. I'm probably just going to use a cosine, which would make my du a negative sine, which means all I need to do now is just move that negative over to get negative du is equal to sine of x dx. Okay, so I'm not replacing this with just a du, it will be a negative du. Okay, that always happens if you actually break off the sine instead of the cosine. Okay, so if you break off the Cosine, you don't have to worry about that. But if you break off the sine, you know, it will come into play. So this one, it would probably be better practice and maybe easier on us if we broke off the cosine instead. At the end of the day, it doesn't matter. And if the sine is your only odd power, then you have to, you know, use it. So, okay. Now, that means I want this integral that we have left, I basically want it just in terms of cosine, because that's going to be our u, right? So we want this just in terms of cosine. So it's really the sine to the 10th that we want to mess with. Now there are multiple ways we could go about doing this. Okay, the way I'm going to do it is I'm going to rewrite this as this is sine squared of x all raised to the 5th. Okay, because the 5 times the 2 would give us the 10. So we have sine squared of x raised to the 5th times cosine to the 17th of x. We're not going to mess with that because that is already how we want it. This is already just u to the 17th. Okay, then we have the sine x dx. We're not going to mess with that either because that is our negative du. All right, now here we're going to use the Pythagorean identity. And I'll just put Pyth-ide, all right, just to simplify our life a little bit. And the Pythagorean identity is going to make that 1 minus cosine squared, because the Pythagorean identity always changes one of your trig squareds into terms of the other. So I have 1 minus cosine squared all to the 5th times cosine to the 17th x times sine of x dx. All right, now here's what I'm going to do. We could expand this all out with cosines and whatnot, you know, to the 5th. That doesn't sound nice to me. So I'm going to actually convert into u's now. So this would be our u to the 17th. Now what we have here is 1 minus u squared to the 5th. And it'd be much easier to expand that out, and then this will be negative du. So when I do this, I'm going to take that negative all the way out to the beginning. Right? So we'll get negative the integral of 1 minus u squared all raised to the 5th times u to the 17th du. Okay, so that negative du, I just moved the negative outside just so I don't have to worry about it. Okay, now we're going to expand this monster out. Now, when I have to expand out something like this, a binomial to the 5th power, what I do is I go to the, I'm blanking on the name right now, Pascal's triangle. Yeah, I start setting up Pascal's triangle. So this would be like to the 0 power, to the 1 power, to the 2 power, to the 3 power. All right, to the 4 power, we will get 1, 4, 6, 4, 1. And to the 5th power, I'll get 1, 5, 10, 10, 5, 1. All right, so what this does is this gives us the coefficients of what this thing would be multiplied all the way out. So if you ever see like a math professor do something like this really quick, just all at once, this is probably what they're doing in their head. Okay, so it's going to be the coefficient 1 times 1 to the 5th. Okay, then it will be, now we have to be a little careful because this is going, we have to set this up as a 1 plus a negative u. Right, so what we have to be careful about is this minus sign. Okay, so think of it when we do this as 1 plus a negative u squared. We often don't have something actually squared in here when we do this. Okay, so we just need to make sure we put it in where needed. All right, so this will be the coefficient 1 times 1 to the 5th. All right, then it'll be plus 5 times 1 to the 4th times negative u squared to the 1. Okay, now there are a lot of ways you could go about this. This is going to be a bit of a pain in the butt no matter how you decide to do it. But I prefer to use Pascal's triangle. Then it'll be plus 10 times 1 to the 3rd. So notice the exponent of the first guy is going down while the exponent of the second guy is going to be going up. Okay, so it'll be plus 10 times 1 to the 3rd times negative u squared, all squared. Okay, then it will be plus 10 again times 1 squared times negative u squared to the 3rd plus, running out of space here, but then plus 5, I'm at the 5 point, then 1 to the 1. So in our next step, the 1 piece is going to disappear while we'll get our negative u squared piece up to the 5th power. Okay, so let me continue this right here as now that we'll have plus 1. Okay, then the 1 to the 0 we don't worry about, and this will be negative u squared to the 5th power. Okay, not the pleasantest thing in the world, but hopefully this kind of shows how out of control these trig things can get, despite how simple it may have looked originally. Okay, so let's simplify this down, because right now this is a big mess. All right, so we'll have 1 plus, all right, here the negative will stick around, so we'll get negative 5 u squared. Okay, for this piece, now the negative should disappear because we're squaring it. So we'll get plus 10 u to the 4th. Okay, then here, on the other hand, the minus should stick around because we're cubing it, and cubing a negative, it keeps the negative around, so it'll be negative 10 u to the 6th. All right, then here, when we get to the u squared negative to the 4th, the negative should now disappear. So it should be 5 u to the 8th. And then finally here, since we're raising that negative u squared to the 5th, the negative should stick around, and it'll be negative u to the 10th. Okay, pretty terrible, but we're getting it much more simplified. Okay, so now what we're going to do is distribute this u to the 17th over to everything. All right, so when we do that, we'll get negative. It'll be u to the 17th, okay, minus 5. Now this will be u to the 19th plus 10 u to the, what would that be, 21 minus 10 u to the 23 plus 5 u to the, I think that'll be 25, and then minus u to the 27, if I did all of that correctly. Okay, then now I'm just going to distribute that minus sign back through just so I don't have to worry about it anymore, or so I won't forget it, right? That could also be a possibility, because all we're doing here is just changing every sign. And which I forgot to do there. So yeah, this stuff can get really out of hand really fast. But we're almost done. Now we just integrate all this, but it's all power rules now. Okay? So it'll be negative u to the 18th over 18. Okay? Plus, it'll be 5 u to the 20 over 20. So this one will actually simplify all right. That's not too bad. Negative 10 u to the 22 over 22 plus 10 u to the 24 over 24 minus be 5 u to the 26 over 26 plus now it will be u to the 28 over 28 and all plus c. Okay, but this is kind of a mess. We could factor out maybe a u to the 18th, or we could just plug it all in and get what we get. So let's go all the way back and remember what our u was. Our u was cosine x. All right, so now we'll just put our cosine x's back in. And so we'll get negative 1/18 cosine to the 18 of x. Okay, now the 5 and the 20 will just end up with a 1/4 cosine raised to the 20 of x. Okay, minus, we could take a 2 out of both of these and get a 5 over 11. Not u, cosine to the 22 of x. Okay, we can take 2's out of this and get 5/12. Did it again, cosine to the 24. Let me finish it off down here. Minus 5/26. I don't think that simplifies at all. Cosine to the 26 of x. And then plus 1/28 cosine to the 28 of x plus c. Whew, okay, got it. I'm not going to double check to make sure that this works in the opposite direction because just look at this thing. But these integrals, these cosine times sine raised to powers, they can get out of hand really fast. All right, so sorry about that, but that's just the way it goes. Let's now take a look at the other piece because unfortunately it can get just as out of hand as this one does. All right, so here's an example where both of our exponents are even. Okay, so all even exponents, what we have to do here, we can't break a piece off, right, because we wouldn't be able to set up anything that would work for us. So what we have to do is use the half angle identity or identities multiple times until we get something we can integrate. All right, so and some of you may be asking, well, how do we know? And in this case, what this means is when all of our powers are gone. All right, so what we do is we use the half angle identities multiple times. Okay, so we use the half angle on cosine squared. So I like to write it with this already factored out form as the 1/2 times 1 minus, or with cosine, it will be plus 1 plus cosine of 2x. And then here the 1/2 1 minus cosine of 2x dx. Okay. And the reason I like it factored out already is it just saves me a step. I don't have to factor or anything. So I can move the constant all the way out. 1/2 times 1/2 is 1/4. So I'll have 1/4 times the integral of this 1 plus a cosine of 2x and a 1 minus a cosine of 2x. Now, here's where it's nice to know our difference of squares, because the difference of squares, when we multiply this all out, the middle term disappears, and so we'll get 1/4 times the integral of 1 minus cosine squared of 2x dx. Okay? Now from here, you might think, well, oh, I could use a Pythagorean identity and move that down to a sine, but don't, I mean, you could, right? But I wouldn't think that way, okay? What we're going to do instead is now, since I have another cosine squared and the exponent is even, we're going to do another half angle. Now, what I mentioned before is doing the Pythagorean identity. You could do that, but you'd have to do another half angle anyway. So, you know, you're just adding extra steps. Now, here's where we need to be careful. Here, we had 1's sitting in front of our x. So when we do the half angle identity, we go from a 1x to a 2x. Okay, so we're always multiplying by 2 on the inside. So I'll say multiply by 2 on the inside. And the reason we need to be careful about that is because we're starting with a 2, and so when we do the half angle identity, we should get a 4x on the inside. All right, so we'll get 1/4 times the integral of 1 minus, now it'll be 1/2 times, then another, it'll be 1 minus cosine in here of 4x. Okay, and all of this dx. All right, and now this should be what we're able to integrate, okay, because we got rid of all the powers, but well, we still need to simplify this a bit before we get anywhere. So let's distribute this negative 1/2. So I'll get 1 minus a half plus 1/2 times cosine of 4x. Okay, I want to simplify this a little bit more because this 1 minus a half, that's going to be just a half. So we'll get 1/4 times the integral of a half plus a half cosine of 4x dx. And I'm going to take that, I'm going to factor this 1/2 out because they both share 1/2, so I'll factor that out to get 1/8 times the integral of just 1 plus cosine of 4x dx. All right, and now we should be able to integrate this. Again, how I know that is I got rid of all the powers of my trig functions, of my cosine. Okay, so it'll be 1/8 times, now we just integrate. Integral of x, or excuse me, of 1 is x. Integral of cosine of 4x, now don't forget this, is going to be 1/4 sine of 4x. Okay, plus c. And as far as I'm concerned, this right here is good. We could leave it like this, or we could distribute that 1/8 back through, but I don't, I mean, it might make it look a little nicer, but I consider this good. Okay, so here we have sine to the 6th of x, and notice we don't have a cosine here, but the only power of sine that we have is even. So the even power, it means we need to do the half angle. Now we can't do it yet because we need sine squared to do the half angle identity. So I'm going to rewrite this as sine squared of x all to the third. Okay, and then do the half angle identity on the inside here. Okay, so we'll get the integral of, now for sine squared, it's 1/2 times 1 minus cosine of 2x, right? And then we are cubing this whole thing. And I think I need another, yes, another parentheses. Okay? Now, when we do this, I need to cube the 1/2 and this whole thing. Okay? So the 1/2 cubed will be 1/8. So I'll bring that 1/8 to the outside. And let me just rewrite this as 1 minus cosine of 2x all cubed. And this is really why I like the completely factored version of this. It saves us some time, right? It saves us a step. And considering how many steps these take, that can be a huge deal. All right? So, I need that 1/8. And now I'm going to distribute this all out, and I go to my Pascal's triangle and realize that the squared is the 1, 2, 1, while the cubed is the 1, 3, 3, 1. Okay, so this should be 1, right, plus 3. So this would be 1 times 1, let me write it cubed, 3 times 1 squared times, now we have to introduce this negative because this is a plus negative cosine of 2x like we did last time. Okay, so it'll be minus cosine of 2x to the 1, okay, plus 3 times 1 squared. Again, normally you wouldn't write all this, I'm just kind of showing where this junk comes from, times negative cosine of 2x all squared, then plus 1, and then here the, I think, yep, I sure did mess this up. That should be 1 to the 1. Okay, then it'll be times, well, the 1 piece disappears, but the negative cosine of 2x gets cubed. All right, now we'll get 1/8 integral of 1. Here we'll get minus 3 cosine of 2x. Now this piece right here is ready to integrate, no problem. This piece, however, will become a plus 3 cosine squared of 2x. Now this is not ready to integrate. And then even worse, here we get a minus cosine cubed of 2x. Okay, now this brings us into some funky integral stuff because here we're going to need to do another half angle identity. So what we have is that this piece of the integral is ready to go. This is ready to integrate. This piece is not. This is another even power. And this one is not, but this is an odd power. Well, remember with odd powers what we did is we set up a U substitution by breaking a piece off. Okay, so what we're going to want to do is split this integral, I won't say down the middle, but break it in half. So here we'll do a half angle. Okay, and here we'll do, we'll break a cosine off. Okay, so let's go ahead and do that in this next step. I'll keep this 1/8 sitting outside. Now the integral of 1 minus 3 cosine of 2x. Okay, and then here we're going to do another half angle identity. So I'll say it's 3/2, right, because we have the 1/2, times 1 plus cosine of 4x. So remember, we're always doubling what's already there. So we went from 1 to 2, then from 2 to 4. Okay, and so this is basically ready to integrate. Okay, all we need to really do is simplify. So this is ready to go after a simplification. Okay, what I'm going to do here is, now the one thing you should not forget if you're doing this should be minus 1/8. That 1/8 still comes along there when you split this integral up. And I'll have cosine squared of 2x. And shift this over a little bit. Times cosine of 2x dx. Okay, so this is what I want to be our du. So notice this particular example, we ended up using both methods because the odd power showed up partway through. All right, so here let's simplify this a little bit. I have a 1 plus a 3/2, so that's of course 2/2, so that should come out to be 5/2. So I have 1/8 integral of 5/2 minus 3 cosine of 2x plus 3/2 cosine of 4x. Notice we cannot combine these as like terms because this is a 2x and this is a 4x. Okay. Now here, with our setup here, we want our du to be this cosine of 2x, which means we want our u to be sine of 2x. Well, when we do that, we actually get a 2 that shows up. Okay? Sine of x, its derivative is 2 cosine of 2x. So really what we're doing is we're using 1/2. That's probably not a good way to leave that. We're doing 1/2 du is equal to cosine of 2x. So this will actually be a 1/2 du. All right, all these fractions get to be worked in. And then this is not in terms of sine at all, so we have to use the Pythagorean identity. Okay, so let me write this in orange. I'm going to do the Pythagorean identity, so that makes that 1 minus sine squared of 2x. I'm going to leave this as it is, cosine of 2x dx. All right, and sorry about the sloppiness here, but now this will become our u squared. This will become our 1/2 du, and we can still mess with this. All right, I'm going to, again, we have a lot of junk in here, but I'll go ahead and say that this is 1/8, and then we'll integrate this piece now. Oops. So it'll be 5/2 x minus the integral cosine of 2x is 1/2 sine of 2x. Okay. Then here we'll just do a 1/4 instead, so it'll be 3/8 sine of 4x. Okay. Then here, when we set up the u substitution, the 1/2 du, I'll go ahead and bring that 1/2 outside, so it'll be 1/16. Okay, integral of 1 minus u squared du. And we're almost done. This part is just going to basically remain the same. I can distribute that 1/8 if I want to and get 5/16 x minus 3/16 sine of 2x, okay, plus 3/72, or 3/72 sine of 4x. Sorry, I don't know where 72 came from. That should be 64 sine of 4x. Then minus 1/16. Then we're going to integrate this guy. It's u minus 1/3 u cubed. And then we can put the plus c. And then all we need to do to finish this off finally, let's just copy this. blah, 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 blah. Now I'll put the our u back in. So our u, if we remember what that was sine of 2x. So this will be sine of 2x, okay, minus a third sine cubed of 2x. Finish that off and put a plus c. Now, I could distribute this, I could combine like terms, I could simplify. I'm not going to bother. I'm going to say this is done. For the record, you can put answers like this into MyLabs Plus, or MyLab Math, okay? It will take this. So don't, honestly, I would not waste my time simplifying this all the way down if I didn't have to. Now that we've gotten through the sine and cosine, we see how just out of control they can get and how quickly. I wanted to talk a bit about tan and secant. And if you have a tan to the power times secant to the power, the process is really similar, but it's a little more specific in how the powers have to be. But essentially, if the power of secant is even, so that's, I matched it up here, tan to the t power, secant to the s power. If secant's power is even and positive, what you do is you break off a secant squared. And then you do the same thing you were doing before, using u equal to tan of x. On the other hand, if the power of tangent is odd and positive, you break off a secant x, tangent x, and here, in this case, you would use your u, set up your u substitution with a secant x as your u, and then the secant x tan x as your du. Right? So this would, here, in this case, that would be your du. Here, this would be your du. The third case, if you don't get either of these, so if t is even and s is odd, you basically have to make a polynomial in terms of secant and use a reduction formula. So that would be like number 4, the number 4 reduction formula on page 534 of your book. This form is not something I would say ask on a quiz, but if you come across an integral of this type, this is really all we have. And the reduction formulas are essentially basically a simplification of by parts. They use by parts to help with this. So we'll look at an example of that. But first, let's just look at an example of one of these simpler types that we could tackle. All right, so what we have here, we see this isn't actually that bad. A lot of times these tan and secant ones come out to be a bit nicer than the sine and cosine ones, because here we have an even power of secant squared, and not just that, or sorry, of secant, but we have secant squared. And secant squared, this is the derivative of tan all by itself. Whoops, not tax, tan. So if we let u be tangent of x, then du would be secant squared dx. And so that makes this whole thing du. Now, you may have actually seen an integral like this in Calculus 1 even. When you first learn about your u substitution, this is a pretty standard integral, because if tangent is u, then this is just u to the 9th, right? So our new integral really just becomes 10 u to the 9th du. All right, so we integrate that. That'll be 10 u to the 10 over 10, so the 10's cancel, plus c. So we get u to the 10th plus c. And then we just put the tangent back in and get tangent to the 10th of x plus c. All right, so a much nicer one than the ones we've been looking at so far. So given that, let's look at another one. Okay, let's take a look at this one. Here we have tan to the 5th theta times secant to the 4th theta. So here what we have is the s even. Okay, but we also have the t odd. So we could actually sort of tackle this in multiple ways. Let's start by breaking off a secant squared. So let's break off secant squared. Okay, so I'll get tan to the 5th theta. And then we'll have, when we break off the secant squared, a secant squared theta times a secant squared theta. Okay? Now, remember, whenever we break off that piece, this is what we want to be our du. So here, we want our u to be tangent of theta. And that would make our du secant squared theta d theta. Now, in this case, very similar, okay, to what we were doing in the past, we need this thing completely in terms of tangent. So we need to transfer this to a tangent, right? And we do that with a Pythagorean identity. Right, so again, once you have the technique down, it works. Okay, you do it the same way you do the sine and cosine ones, but it might be a little more tricky with these secants. But you might not remember that there is a Pythagorean identity involving secants and tangents. Right, if you have sine squared theta plus cosine squared theta equals 1, what you can do is divide everything by cosine squared theta, and get the Pythagorean identity in terms of secant and tangent. Specifically, sine over cosine, that will give us a tangent squared. This will give us cosine squared over cosine squared is 1. And 1 over cosine, well, that's secant. So it turns out that secant squared theta is tangent squared theta plus 1. All right, so with the Pythagorean identity, we get this new integral, tan to the 5th theta, okay, times tan squared theta plus 1 times secant squared theta d theta. Okay, now I'm not being very consistent with my parentheses here. Now I'm going to do our u substitution, right? This will be u to the 5th, this will be u squared plus 1, and this will be our du. Okay, so our new integral will be u to the 5th times u squared plus 1 times du. Right, and so we'll distribute this u to the 5th to get the integral of u to the 7th plus u to the 5th du. And now it's just essentially power rules. So now we just put, in this case, our thetas back in. So it'll be 1/8 tan to the 8th theta plus 1/6 tan to the 6th theta plus c. And there we go. Okay, so it's a similar process as before. All right, so we could have actually also approached this in the way with the tan being odd, its power being odd, by breaking off a secant x tangent x. So break off a secant, in this case theta, tangent theta, and let that be our du so that our u is secant theta. Okay, so let's try that. All right, if we break off a tangent, we'll get tangent to the 4th. All right, we break off a secant, we'll get secant cubed. Okay, and then we will get secant theta, tangent theta, d theta, and this is what we want to be our du. Okay, which makes our u, of course, secant. All right, but like before, we need to get this guy in terms of just secant. Okay, so we need to use the Pythagorean identity here. Okay, so remember our Pythagorean identity was tangent squared theta plus 1 equals secant squared theta. So that makes tan squared theta equal to secant squared theta minus 1. Right, but notice we have tangent to the fourth, so that's tangent squared squared. So this will be tangent squared theta all squared. I'm going to stop putting all the parentheses just to speed things up a little bit. All right, so here, this is still our du. This right here will be u cubed, and this right here we're going to use the Pythagorean identity on. Okay, so we'll get that tan squared is secant squared theta minus 1 all squared times secant cubed theta times secant theta tangent theta d theta. And now I could FOIL this out with the secants, but like last time, I'm going to go ahead and get this new integral in terms of u. So secant squared will become u squared. The 1 just stays as 1. Secant cubed becomes u cubed. And this secant theta, tan theta, d theta, that just becomes our du. Okay? And now we can FOIL this out. This will be u to the fourth minus 2u squared plus 1 all times u cubed du. Okay? And from here, we just distribute that u cubed, and we'll get u to the seventh minus 2u to the fifth plus u cubed du. And at this point, I think we've done this enough times that I think you can probably finish it from here, right? Do your power rules, put your secant theta back in. All right, so here's an example where we might have to use a reduction formula, because what we have here is our s is odd. And even if we thought, oh, well, what, tangent, we could say that this is tangent 0, because anything to the 0 power is 1, but 0 is even. So this is essentially like, okay, we have an odd power of our secant, so we can't break off the things that we need. All right, so we'll have to use a reduction formula. And if I look at that page number in the book that I mentioned earlier, we can get the number 4 reduction. Okay, let me look that up real quick. All right, so here's the reduction formula for secant. It's secant to some power n x dx. That integral is secant to the n minus 1 of x times tangent x all over n minus 1 plus n minus 2 over n minus 1 integral secant n minus 2 x dx. All right, this is essentially using by parts, okay, and it's giving us a formula that's we could just look up. Notice I don't have this memorized, okay? Most people I don't think have these reduction formulas memorized. I don't expect you to have them memorized, and that's why, like on a quiz, I wouldn't give you one that would require this. However, for the homework, just so you maybe know where to look, know what to know how to handle problems like this, we just fill our pieces in to this reduction formula, right? So in this case, our n is 3. So applying this reduction formula, it will be secant to the n minus 1, so that'll be secant squared of x, and in this case, sorry, we're using theta, times tangent theta, all over n minus 1, which is 2, plus n minus 2, which will be 1, over n minus 1, which will be 2. So it'll be 1/2 times the integral of secant to the n minus 2. So secant to the 1, so just secant theta d theta. Okay? So we've simplified this quite a bit. Notice these reduction formulas aren't as nice as you might think, because now we have to deal with this integral here. All right, and this is another odd power of secant, secant to the 1. We can't use this reduction formula again because n minus 1 would be 0, so we'd be dividing by zeros. So actually, we haven't talked about this yet, but the integral here can be found by a funky version of 1. If you remember our advanced techniques, we're going to use a funky 1 here, and it's actually kind of tricky version of 1. Okay, because what we do is we multiply this by secant theta plus tangent theta. And you might think, well, why in the world is that our funky version of 1? And it's mainly because it's magic and it works. All right, so we're just going to copy this piece down. And when we distribute across the top here, so this is secant over 1 times this thing here. When we distribute, we'll get secant squared, okay, plus secant theta tangent theta. Let's get rid of that. All over secant theta plus tan theta, and this whole thing d theta. Okay. Now, again, this part stays the same. Tangent theta all over 2 plus 1/2. And here we go. Here, this is just a u substitution, because if we let the denominator be u, right, so if u is secant theta plus tangent theta, well, that's going to make du. Well, the derivative of secant is secant theta tangent theta. And the derivative of tangent is secant squared theta. Well, that's our numerator. So this altogether is going to be our du. So we basically have 1 over u du. All right? And so that gives us 1/2 natural log absolute value of u plus c. And then when we put our thetas back in, we'll get 1/2 natural log absolute value of secant theta plus tangent theta plus c. Okay, now that we've done this work, we don't have to do this again. All right, so that tells us that we now have a rule that we could just apply, that the integral of secant theta d theta is the natural log of the absolute value of secant theta plus tangent theta. Okay, so that'll help you out if you know that one. And actually, if we do a similar u substitution, we can find the integral for tangent, which you've probably done in Calculus 1, but there's an extra simplification that we do to give us that the integral of tangent theta is the natural log, the absolute value of secant plus c. All right. So to me, this does kind of make sense, because if we think that the derivative of secant is secant x times tangent x, then the integral is the natural log of secant theta plus tangent theta, and the integral of tangent, so if the derivative went to secant squared, its integral goes to the natural log of secant theta. So we have the same pieces, just when we integrate, it is put into the natural logs. Okay, so yeah, All right, that is definitely enough for this particular video. So I'm going to leave it there, and I will talk to you all for the next one. Cheers.